The geometry of all the physical constants, Coulomb's constant, Newton's gravitation, the speed of light, even the relationship, Einstein's relationship or equivalence between mass and matter, or mass and energy, can all be traced back to the equilateral geometry of energy itself. In the case of Coulomb's constant and Newton's gravitational constant, the superpositioned energy fields between the sources of charge or the sources of mass are in fact equilateral fields. They're the KEM fields of the objects in motion, or their radiant energy, and the superpositioning of those fields creates superpositioned energy momenta, and that's where the force between charges comes from. That's where the gravitational force comes from. So all equilateral geometry gives us a basis for our constants. The first one that we've just been discussing earlier today was Planck's constant, where we revealed that the equilateral geometry in this case is a measure of square meters. So when we measure the square meters, or the geometry of the energy per second, we get the quantized angular momentum. And likewise, measuring the energy content of that same equilateral triangle per c squared, or per second, gives us mass. So together with the scalar energy content and the equilateral geometry, we end up with a unit of mass square meters per second, or Planck's constant. That's the units of Planck's constant. Tetryonics allows us to calculate the mass of the matter of hydrogen, a number of other constants as we'll go through, but in the case of Planck's constant, investigation and refinement of Tetrayonic theory has given us an exact value for Planck's constant of 3.629697947 by 10 to the minus 34 joule seconds. Slightly different to what's currently accepted, but when you use this exact formula derived from the rest matter of hydrogen, i.e. an electron and a proton with no kinetic energy, we can then calculate Avogadro's number exactly, and we can also create or calculate exact rest masses for all the periodic elements. So once again, Planck's constant, which has had various values over the years but all around the same amount, is now refined to what's on this page as an exact value for the energy angular, or the mass angular momentum content of equilateral energy. And it's that constant that gives us the building blocks of all mass, energy and matter. Coulomb's constant, as I noted on the opening page, is simply the result of two KEM fields, or two electrostatic charge fields, superpositioned between two particles. So if you have two particles of matter both generating either energy fields through their motion or electrostatic charge fields, these fields radiate out from those objects of matter until they encounter other objects, and the fields from both objects overlap each other. Simplified here with both particles close and pointing towards each other, but in all cases the overlap fields all contain individual or large numbers of polarized energy momenta pointing in different directions. In the case of negative fields, the negative points out. In the case of positive, the positive points out. But in both cases, even though they're missing from this page, the opposite charge fields points in the opposite direction. These overlapping fields then push or pull through the law of interaction on other charged objects in that field. So in the case of two negative charges where they overlap, if a negative charged object enters the charged field, the negative energy momenta pointing outwards of the negative source will push that negative object away. Whereas if a positive was to enter that field, that same field, the negative energy momenta would be pushing away, but the positive energy momenta would pull the positive charge towards the negative object. So that creates our familiar laws of attraction. And as you see noted on this picture, similars repel, opposites attract, purely through the energy momenta of the KEM field in each case. Now, measuring the square root of these superposition fields gives us Coulomb's constant, which you'll note has a value, and it has units of Newton meters squared per Coulomb squared, which, if you take the square root of them, is just Newton meters per Coulomb, which is linear momentum per charge, or force per charge, again linear momentum per KEM field. So we can see from a mathematical perspective as well as a physical interaction perspective, equilateral KEM fields that are superpositioned gives us not only Coulomb's constant, but all the forces of interaction between mass and matter. The speed of energy, as we've touched on another video, is derived directly from the equilateral geometry of energy, namely when measured per unit of time, a c² radial measurement of the energy geometry gives us mass, or electromagnetic mass in this case, because you've got electric fields and magnetic fields highlighted. In the case of light, as you'll note down the bottom right, there will be 2 pi geometries, or energy geometries, forming the photon, but it applies equally for light as it does for charge. So that the main diagram is a picture of charge, where we have the inverse of c², or the inverse of a second measurement. So inverting the circle, the c², we have an equilateral triangle of energy. Taking the square root of 1 over c², we have the vector momentum of that energy, in this case charge energy. So the energy momenta heads off in the one direction. In the case of a photon, it would head both directions as illustrated, but that energy momenta will travel at a velocity, in this case determined, has been named the speed of light. More appropriately, it's called in Tetryonics the natural velocity of energy, or the natural speed of energy, purely because sufficient energy, if you apply sufficient energy to that energy triangle, you can in fact exceed the velocity of light for a period until it reaches a critical density, in which case it then resumes travelling at c within a vacuum. So that the constant speed of light is purely a result of its energy geometry within time measurements. Quantum masses, there's a number of ways to calculate what mass is. Obviously, it's by definition it's just a time measurement of the equilateral energy in any system. You can measure it through Planck's constant, you can measure it through the scalar relationship between energy and velocity, or using Tetryonics, as you'll note on the right hand side there, we can actually calculate the exact energy content of hydrogen and an electron geometry. Adding the two together, obviously it's the geometry of hydrogen, and then we can divide the whole thing by c² to give us mass. By aiming to calculate for Avogadro's number, which is the inverse of a hydrogen mass, or the mass of hydrogen matter more correctly, we can then start to adjust and calculate for an exact mass for Planck's constant and for other atomic measurements, purely on the definition of the geometry and physics of the hydrogen atom. For example, what we do is we calculate for a hydrogen, for a proton and an electron at rest energies with no kinetic energy whatsoever. It's a non-natural state, because normally when the electron binds with the proton it will start to spin, but in this case we go for exactly 0. We then calculate the mass for that amount and we multiply it by Avogadro's number, it'll in turn give us another number. We can then calculate all that out so that we get exactly 1 gram for a molar mass of hydrogen. That's then confirmed when we invert that, as I've mentioned, to give us Avogadro's number in itself. Most measurements of hydrogen will of course include kinetic energy, so from a physical perspective you can't calculate for the rest matter or rest mass matter of a hydrogen atom by itself by physical measurements. We can then apply the calculation of a Planck mass to all our geometries in physics, giving us exact rest mass matter for every particle. And then using that knowledge we can also calculate the kinetic energies of any particles that we measure in a system in real life, and then subtract their rest mass matters to give us their kinetic energies. And that's done on that page. Each rest matter for all those items are done. This one we've already touched on. Again, just to touch on mass and matter, the rest matter aspect. Rest matter is defined as the standing wave geometry of any matter, exclusive of any kinetic energies and magnetic moments. Whereas electromagnetic mass, by definition, is constantly in motion. It's not a standing wave geometry. So its energy content while it's in motion can obviously be determined by its energy content, its mass content. Its mass can be determined by its energy content per unit time. Pick a unit of time, measure the energy content, and you'll know the mass content of it. Most, or throughout Tetryonics, you'll see mass is defined as n pi, matter is defined as t pi. The strict definition is where you see t pi, unless it has plus kinetic energy or plus n pi somewhere else in the unified field equation, it's considered to be rest matter without kinetic energy. It's the standing wave form. The middle part of this page purely indicates what's been touched on with the Higgs field boson and things like that. All matter is an electromagnetic geometry. It's a standing wave made up of tetrahedral geometries, but they all possess volume. Whereas in that same picture you'll see a thin blue line which represents an electromagnetic field. It has no volume. So as it moves through the vacuum energies of space, wherever it may be, matter has charged fascia which interact at varying angles to the energy field that surrounds everything, whereas light passes straight through that energy field within reason, has far less interaction compared to that of matter. The inductive or charged fascia, the Higgs bosons that form matter, are all inductive and they all resist change. That gives us the property of mass, and specifically inertial mass, as matter tries to move through any region of space. All of space has electromagnetic fields or vacuum energies within it. It's never truly empty, and it's the charged geometry of matter that creates a resistance along with the energy content of its charged geometry that gives us inertial mass, in the distinction between mass and matter. Again, invariant rest matter is exactly that. The rest matter content, rest mass content of matter does not change when the velocity of the matter is accelerated. The energy, or the kinetic energy of motion, goes into the energy field surrounding the matter. In this case there's a picture of an electron with its kinetic energy field at the bottom center of the page. By itself, as illustrated at the top left, we can now calculate for the mass content of an electron's matter geometry we can then also measure that same electron in motion, giving us a relativistic energy, and we know the difference between the two is purely the energy contained in its KEM field. The energy that goes into the KEM field to accelerate an electron is what is contracted. Specifically, its wavelength is contracted. The matter content, or the mass content of its matter, is not affected by motion. In this respect, relativity, specifically special relativity, has been proven to be incorrect. Again, just touching on the rotation of electrons within nuclei. Here we have two atomic nuclei down the bottom, two deuterium nuclei with electrons in them. The electron can spin in either direction when it binds with the positive deuterium nuclei to create a neutral deuterium atom. If it spins up or down, the terminology up or down does not refer to whether it's spinning up or down on the page. It refers to the orientation of its north-south, of the electron's north-south magnetic moment, or its dipole, compared to the north-south direction of the atom's magnetic dipole. You'll see in the center of the page there's a P for a positive charged proton. Perhaps I should have written deuterium, but proton's still the same. You'll see that its orientation of a south-north pointing downwards indicates the direction that the deuterium atom is moving when the electron binds with it, and then based on which way the electron spins in that atom, you'll either have, in the case of the left-hand side, you've got the same south-north orientation, so it's what's called a parallel spin, versus the north-south, where it's spinning in the other direction, which is an anti-parallel magnetic moment. The terminology is something that's grown up out of quantum mechanics. Basically, a parallel just means that the north-south are both aligned the same way. They are marked, they're called an upspin because they, having the south poles against each other, puts more energy into a system. It means when the electron tries to slow down, those two south poles and the two north poles are going to push that electron away with more energy than it would have if it was trying to hold them together. So when the electron jumps out of its orbit, it'll have less energy or more energy. In the case of less energy, it was an anti-parallel spin. In the case of more energy, it was a parallel spin. We'll get into that a little bit further on, but that's the crux of the parallel and anti-parallel spins. They are a physical spin in the case of an electron. The electron itself acts like a quantum three-pole or three-phase rotor in a generator. As it spins, its fascia cut through the vacuum energies of space and create the kinetic energy field. That's why the electron's field is far stronger for its size and mass than the proton's field, even though they have the same charge and the proton is physically larger with more mass. The electron generates a stronger KEM field because it is physically shaped like a electromagnetic rotor, so it's far more efficient at extracting energy out of the vacuum and creating a strong KEM field with a strong magnetic dipole from its motion. In this case, we've again modelled all four leptons with the Tetryonic geometry for charged particles in motion. And then through the center of the page at the angle, you can see as the electron accelerates, it gains increasing square energy within its KEM field. The mass and the geometry of the electron does not change. Only the energy content or the mass content of the KEM fields change as the electron accelerates through the field. That same acceleration and addition of energy or mass energy to the KEM field is what creates the three distinct families of leptons, as in electrons, muons, and tauons. That same energy content of KEM fields is what creates the neutrino oscillation of neutrinos when they come from the sun. When the sun first accelerates the neutrinos, it creates them within its own energy environment and gives them a lot of energy to accelerate them towards the Earth. They come shooting out with a huge amount of energy, a huge chem field, but their mass matter, is identical in all cases. As they get closer and are slowly slowed down as they interact with particle detectors on Earth, they give up their chem field energies, and this is seen as an oscillation between different families of neutrinos, when in fact all it is just a loss of energy in their kinetic energy field between when they're created and when they're detected on Earth. Again, this is a closer picture of that exact same explanation. As energy is added to the leptons, they start off as electron particles. They then have an increased mass energy in their chem fields and become muon electrons, muon neutrinos, anti-muons, and then with even more energy they become taus and tau neutrinos and anti-tau particles. Strip the anti-taus and the tau neutrinos of their kinetic energy fields, and you will have positrons, neutrinos, and electrons. They're all the same particle. All that's changing is the energy content of their kinetic energy field as they're accelerated and detected. Same thing happens with electrons in atoms. As electrons bind to atoms or nuclei of different energy levels, they spin at different rates accordingly. The main picture on that page in the center is the picture of the electron with its kinetic energy field. You can see I've described it as being either measured as Planck's constant by the frequency of the photons, or you can measure it in electron volts. Either measurement is a measure of the energy content of the chem field. The chem field, as it states there in the formula, is mv squared because it's an equilateral geometry. And it's equivalent to HF, although you will find, because of its equilateral geometry, some of the frequency will be half wavelengths at the base of that triangle, because in reality they're all equilateral geometries. Of note here is the energy levels of atomic nuclei that these electrons bind into to get their increasing rates of spin. You can see that in each picture, as the energy level of the nuclei and the electron are increasing, they're increasing because there's a number of nuclei under each atom that it binds to. You can think of deuterium nuclei as a quantum battery. They've got a plus and a minus end, proton and neutron. They have a slot for electrons to bind into them. They can store energy as mass, and the energy that they store when the electron slots into them causes the electron to spin, just like plugging a light bulb into a light socket or plug it into a battery. Hold it on a 3-volt battery, it glows a certain amount. Put two 3-volt batteries together and you'll have a brighter glowing light bulb. Keep adding battery after battery. Each time the light bulb glows brighter. The electron's doing exactly the same thing. As you get more and more nuclei binding together to form more and more larger and larger atomic nuclei, the electron that binds with them at that energy level will spin faster. These energy levels, as depicted here, are often referred to in chemistry as quantum shells. The Bohr radius, currently and for over almost a century now, has been thought of as a change in the orbital radius of an electron away from its nuclei, or away from the proton, i.e. as more energy is added to the electron via light, it jumps to larger and larger atomic nuclei as drawn there in the central picture. In fact, what's happening is the chem field, as illustrated at the top right, is getting more and more equilateral energy quanta added to the field, so that they increase in square number increments. The energy again comes in as odd numbers via bosons. creates square number geometries, and each time the square number increases or decreases, there's more or less energy momenta in that surrounding KEM field, so the electron either speeds up or it slows down. There is no physical jumping from one orbit to the other, which has always perplexed quantum mathematics, because to physically say that 1 second the electron's one size and the next second it's physically jumped to a different spot, a distance away from where it was, without travelling in between, is obviously nonsensical. In this case, what's physically happening is that those energy quanta in the KEM field are increasing in odd number amounts to create different square number energy fields. And those energy fields are the Bohr radius changes, the quantum leaps in atomic nuclei for spectral lines. As you can see here, we've got the two pictures. You can see at the top left-hand picture, on the left-hand side of it, the energy levels ranging from energy level N1, which has just got one energy quanta in it, right down to N8, which would have 64 energy quanta in it. These energy levels respond directly, as noted, to on the right-hand side, to the quantum energies, or the energy of motion of the electrons in the nuclei. Again, we have our middle picture illustrating the various energy levels with their quanta highlighted in colours, with their magnetic moments and kinetic energy fields. But this time we've done the conversion for the energy, or the mass energy, and we've converted it into electron volts. So you can see that if you've got one, or an energy level of 1 with an electron in it, to jump all the way up to more than 64, or more than N8, 64 energy quanta, would require you to add enough equilateral energies to give it at least 13.38 electron volts worth of energy. So in this case, to jump to 65 energy quanta, or which is more than the 64, we would have to put in at least, we've got 1 to start with, we need more than, or we need 63 to get to level 8. To jump past it, we need at least one more energy level, or one more quanta to get past it, which is a minimum of 13.38 electron volts when you do the calculations. These transitions between the square numbers, or the different colour energy levels, N1 to 8, in both directions, are what create spectral lines. All the colours that we see off our clothes, off our torches, off from people's eyes, off objects that we see around us, are all created by electrons transitioning from one energy level to the other, either absorbing the colour or emitting it. They're all described by that formula on the bottom, which is Rydberg's formula for energy transitions. Basically, it gives you the wave number of the light, and that can be used to calculate the wavelength and the frequency of the light that's being generated from those transitions. We'll cover that in a little while. Again, this just highlights that electron spin and tries to stress that electron spin is not not determined by the direction of the electron itself and its spin. It's determined by the magnetic dipole that's created from that spin. So you measure the magnetic moment of the proton, you then measure the magnetic moment of the electron, and if they're both the same way, they're parallel. If they're opposite or reversed, they're anti-parallel, spin up versus spin down. It's illustrated in this picture. That's the essence of it. Even though the direction of the spin dictates which way the north and south are created, it's the measurement of the north and south with respect to the north and south magnetic pole of the proton that determines whether it's a spin up or spin down. You'll find a lot of literature contradicting itself on this, and you'll find a lot of literature trying to explain this as simply as possible. This is the best way I have of illustrating that relationship. Again, same thing here. It's just showing you that In the case of the electron, the illustration at the top right there, the direction of the electron spinning with respect to the Bohr magneton, or the magnetic moment of the particle that's attached to, determines whether it's spin up or spin down. That's the 4 possible combinations you can have, and that same illustration gives you the 4 possible combinations that can be created with positrons, the antimatter equivalents of electrons. So again, just to reinforce it, the direction of spin is neither up or down. What is up or down is the orientation of the magnetic moment of the electron with respect to the magnetic moment of the positron or the magnetic field it's moving through. Same picture again. This time we're illustrating it using the schematics for particles in motion. You'll see in the middle of the bottom box the positive charge schematics for kinetic energy and magnetic moments versus the ones at either side for the electrons moving in either direction. So in this case, that picture at the bottom can show you the direction of motion for the proton and the direction of rotation for the electron, one way or the other, and what spin results due to the orientation of the magnetic dipoles in each case. And again, as shown here at the top right, the electron is far more efficient at creating a KEM field and magnetic moment than the proton is. The proton creates a far weaker one. In fact, the ratio is exactly the same as the mass-matter ratios between protons and electrons, almost a 1 in 2,000 difference. Same picture again of the parallel and anti-parallel Bohr magnetons versus the electron magnetons. In this case, the picture on the right hand side simply shows you the higher and lower energies that are created, with a picture of the normal charting of these energies in the background as they're measured coming off atomic nuclei. So that in the right hand side you'll see that as the proton's moving in one direction, you have parallel and anti-parallel spins with the electrons creating higher or lower energy spectral lines, and if the proton moves in the opposite direction, the spins have to be reversed to have the same energy levels achieved from the electrons. So what it emphasizes is not only is the spin of the electron important, but the direction of angular momentum of the atomic nuclei in atoms is important to determine the energy levels of photons that are emitted, because all the energy of the photons that are emitted is a result of the energy of the electron's KEM field. The KEM field has to change in order to produce the photons. The photons that are emitted by atoms all come from the kinetic energy fields. Matter does not lose mass. Only the KEM energy fields lose mass as the velocity changes. Again, matter is velocity invariant. Gyromagnetic ratio, again, been calculated dozens and dozens of ways. From Tetryonic theory, knowing that the charged 12 pi geometry and the exact rest mass and kinetic masses of protons and electrons, plus the explanation of their spins with respect to each other, you can now get exact answers for the gyromagnetic ratios between electrons and protons to do all our calculations, and they're borne out further in QED as well. Again, stressing that an electron is not a spherical point charge, it's a 12 pi quantum rotor. When it comes to figuring out quantum mechanics, where Einstein and everyone else in particle and CERN all went wrong and continue to go wrong, is that at a fundamental level they don't distinguish between electromagnetic mass and electromagnetic matter. One is a 2D radiant energy form. The other one is a three-dimensional standing wave energy form. And until you distinguish between mass and matter, and how it's created and how it interacts, and particularly its matter's invariant properties compared to with respect to velocity, all the particle accelerator experiments are doing are adding more and more energy to the KEM fields of particles as they're created, in turn creating a particle zoo of increasingly heavy particles and particles that they can't explain. It also results in predicted particles having a mass range, because they can't calculate. If one particle, you can calculate the invariant mass of it, but in the case of a boson, it's mass to start with, it's mass energy, it's not matter. So its mass energy content is determined on its velocity as well as its energy content. So all these things add to the confusion, and why Higgs, even though they can create massive amounts of energy and pour it in for collisions, have to have a range for their results. They can't specify exactly what it should be. That, combined with poor assumptions on the physical makeup of things like neutrons, means that we've had a huge amount of problems trying to define the exact geometries of all of quantum mechanics. Tetryonics overcomes that by being very specific, both in the definition of mass and matter, as well as defining what creates the geometry of matter itself. In the case of particle collision experiments, one of the interesting problems that comes about, and one of the things that a lot of people may well ask, is if everything is made up of tetrons, why haven't we seen them? We've got all these particle experiments, why aren't they popping up in the results as small particles whizzing in and out of the experiments? Well, the answer is quite simple. All the particle experiments are they're basically a measurement of the mass-charge ratio of particles moving in a magnetic field. That's how the detectors work, from the simplest detectors right through to the most advanced ones in place at CERN at the moment. When you do the calculations for a tetryon, it has the potential, in the case of heavier tetrons, to have exactly the same mass-charge ratio as an electron. This small quirk means that, apart from its inertial or its kinetic energy upon impact with the detector, the particle tracks of a tetryon will be identical to the particle tracks of a lepton. So you won't pick the difference between negative tetryons and electrons anywhere in the system. The only way to detect the difference is to actually stop the particles once you've detected them and measure their kinetic energy. In the case of particle detectors, we're too busy trying to look at the curvature that the particle leaves in the magnetic field to gauge its mass and its charge. So the detectors work against us in this case. In summary, for quantum mechanics, energy itself is equilateral. It's composed, as indicated on the left-hand side of the equilateral triangle, of odd-numbered quanta that form energy levels. These sequential energy levels add up to square energy geometries. The energy fields themselves are contained of energy momenta. You can have any number of square energy quanta in a energy field, or a measure of mass, and it's these energy momenta and their direction of orientation that creates our electric fields, our charge fields, and our laws of interaction and laws of force. They're the basis of force fields within particle physics. Tetronic matter, or what's called by physics these days as fermions, particles that can't occupy the same space at the same time, are just tetrahedral standing waves of energy. Each charged fascia can be called a Higgs boson. The energy within any one of those charged fascia is the mass, or contributes to the mass, the total mass of the matter. The matter itself is simply the charge geometry. For example, if you were to look at say the deuterium atom at the top right there, you could say its matter is 36 pi, but the mass of its matter is 45,021 quanta, made up of protons, neutrons and electrons, and you can then break down their quanta into their individual charge geometries. In each case, the charge geometries of all matter are some multiple of 4 pi. So hence why we call it tetraionic matter, because they're all formed from tetraion building blocks, 4 pi geometries. They're 4, 12, 24, 36 and upwards. All periodic elements are 84 pi geometries, or n times 84 pi. Helium is twice times 84 because it's 2 deuterium nuclei combined, unless it's got a charge on it due to lack of electrons. This brings us into electrodynamics for Tetryonics. Quantum mechanics covers the charge geometry of mass, matter and energy. Tetraionic QED covers the charge geometry of mass, matter and matter in motion. So it specifically relates back to the KEM fields and the electrodynamics of electricity and spectral lines. Maxwell was the first one to take Faraday's electric and magnetic fields and combine them all into one unified equation, or in this case a series of 4 semi-unified equations. He molded in with Gauss's law, Faraday's law and Ampere's circuital law to create a set of equations that governs all of electromagnetic light, and by definition electromagnetic radiation as well. Tetryonic geometry gives substance to his equations through the geometry, or the equilateral geometry of energy. We can quickly explain all the features that are expressed in mathematical equations as geometries using Tetryonics equilateral geometry. In the case of Gauss's law, it's quickly shown that the equilateral geometry of square quanta results in imbalance of positive or negative quanta within that geometry. That imbalance of plus or minus charges creates a net charge that's either positive or negative. And these equilateral geometries form the geometry of all matter on which it's expressed. So where it's normally been illustrated as a square integral on a spherical geometry, it is in fact equilateral geometries that form quantum charge. Ampere's law, accordingly, can be drawn geometrically simply by having the KEM fields around charged particles illustrate the direction of charged particles in motion. The KEM field points in the direction of the motion of the charged particle, and the dipole of that field then gives you the surrounding north-south field that's normally worked out using the right-hand law. The separation of charges again is given through equilateral geometries, and that in turn shows us the energy momenta of each charge that creates the electromotive force to drive the electrons, or in this case, or in conventional currents theory, the positrons or protons, around in a circuit. Faraday's law of induction, or electromagnetic induction, can be illustrated here as it's done with the electrostatic, the magnetostatic energy field of a bar magnet. The equilateral geometry shows or reveals the energy momenta in each field, and any electron in a closed circuit moving through that field is subject to the energy momenta of the electric fields of the bar magnet. It's these energy momenta of the normally neutralized E fields of the bar magnet that drive the electron around in a circuit. It's not what special relativity, or how special relativity explains the electromotive force being generated by the difference of perspective of the electric or the magnetic fields. It is a physical electric field that is present in bar magnets, one positive in one direction, a negative in the other. And if you look at the two fields there, even though they're neutralized and not detectable as electric fields, they still contain positive and negative energy momenta, and it's those momenta driving negative charges to the bottom of the page, positive charges to the top, that in turn create or put motion into electrons that are in a inductive loop as it moves around the magnet. The measurement of energy per charge geometry, bearing in mind that charge is just equilateral geometry or quantized angular momentum, square meters per second. So the number of quanta per charge, the number of energy quanta per equilateral geometry per c squared, gives us a unit called voltage. The voltage is the unit of measurement for the pressure, if you like, the energy pressure that can be exerted on unbound charges or charged bodies in a circuit to drive them in one direction or the other, dependent on, again, the energy momenta of the energy in that circuit. This energy is given the unit of joule or unit of work. It's simply a measure of how much energy is contained within the equilateral geometry or the charge of any measured system. It's got units of kilograms square meters per second squared, and alternatively in Tetryonics we then redefine charge as just being a measure of mass, charged mass, positive or negative, per second, or alternatively seconds per charged mass. This is what I'm saying. A Coulomb can be redefined right back down in Tetryonics using geometry as seconds per kilogram, and amperes are kilograms per second, as in the number of charged geometries that go past a point in a circuit per second. If you were to exchange this per second for c squared in relativistic terms, you would then have kilograms per c squared, and you'd end up with a measurement of charge for both. Volts and watts are just a different way. One's measuring the energy available per charge, the other one's measuring the force per charge to move charged particles or electrons in a circuit, or to do work in a circuit. Same units resulting from the same equilateral geometry and energy momenta in that geometry. Both are just calculated different ways at different times in history. Again, you can use the same mnemonic used for force equals ma, or Newton's laws, for voltage, where with Ohm's law, and you have a simple mnemonic for Ohm's law in Tetryonics using Tetryon geometry, along with the energy quanta. All this then leads us into electricity theory, how we measure current, how voltage is created, what it really is, and all the foundations that then lead us right into a better understanding of of electricity, Maxwell's work, and Nikola Tesla's work on longitudinal scalar waves. Michael Faraday started it all off by pointing out that a changing magnetic field produces or has a changing electric field, and vice versa. They're all different aspects of the same geometry. Just like you can't have a magnetic monopole, you cannot have a magnetic field without an electric field. They all result from the same energy geometries. The Poynting field, often referred to in QED as a measure of energy in a circuit, is revealed to be electricity itself. It's the energy momenta that flows nearly instantaneously in a circuit when the circuit is closed. It goes through the circuit, or follows preferentially the circuit path, and provides the energy momenta to drive charged particles in one direction or the other through the circuit from the voltage sources. They again can be represented with equilateral geometries. The electromotive force that drives current or electrons to produce a current in a circuit is created through the separation of charges, where you have a positive charge and a negative charge separated through the physical work done by a generator. The energy from that work becomes equilateral energy momenta in the charged energy field, either positive or negative. Under the second law of Tetryonics, that energy, once it's created, wants to equalize itself, wants to seek a zero state. It will stay as a charged state until you put a conductive circuit in place. When you put the conductive circuit in place, as illustrated in the middle diagram, the charged or free charged matter objects in that conductor will be free to be acted upon by the energy content, or the joules that are contained in the separated charges. Coincidentally, even though a permanent magnet can be viewed as a storage of magnetic fields, it's in fact a storage of electromagnetic fields, and as such can be redrawn simply as a battery of energy, positive and negative charges touching each other to create the magnetic dipole. So the eternal or everlasting supply of energy that comes from bar magnets that keep them on the fridge is suddenly revealed to be the result of equilateral energy geometries, or in this case voltages that have actually reached equilibrium, and when in doing so they've created a magnetic dipole in the metal with neutralized electric fields. Again, if you could separate the atoms that are in a bar magnet to create a true battery, and then place a closed circuit on it to drive electrons in that circuit. The separation of charges creates what are called sinks and sources. It's just a terminology for when you create energy momenta that drives charged particles in one direction or the other. The motion of electrons in a circuit are driven by the direction of negative energy momenta, and they're driven in that direction through the circuit until the number of energy momenta, positive and negative, have equalized in the circuit, at which point the battery is said to be depleted or equalized, and it needs to be recharged. The process of recharging simply adds energy to each voltage side via separation of the charges in one direction or the other, or both. Electricity itself and kinetic or KEM energies. Electricity can now be shown to be the flow of energy momenta in a circuit normally along a conductor, although it can flow in free space between 2 points. Once that energy field is established, whether you call it the pointing field or the electricity field, any charged object in that field will be motivated to move one direction or the other depending on their net charge or their matter geometries. One direction is called electron flow, the other direction is called conventional flow. Again, it's important to point out that even though the mass of the moving electrons changes, it's only the mass of their KEM field that changes because of their motion. The mass matter, or the mass of the matter of an electron, is invariant to its velocity. And in fact, electrons move slower than the electricity in a circuit. Electron volts are simply a measure of the energy within the KEM field of an electron in motion. An electron can come into a circuit at a specific velocity, in which case it has a specific energy related to that velocity, a squared energy field. A generator or a battery can add energy to the kinetic energy field of that electron and accelerate it out back into the circuit, adding any amount of electron volts to that charged particle. And in fact, that's the very basic process of a particle accelerator. One of the final things that come out of Maxwell's equations is displacement current. Maxwell was the first to realize that when that electrons move through a circuit and carry their energy, they can't move through a gap in the circuit, i.e. if you place a capacitor in the circuit, the electrons cannot physically move through the capacitor and out the other side. The capacitor blocks the DC flow of electrons, will only allow AC. As a consequence, he had to create and amend his formulas to include a thing called displacement current, which is just the storage of energy over time, or the storage of energy in a capacitor as charge. As the electron moves towards the capacitor plates, in this case, doesn't matter which direction it moves in, as the electron moves to it and is stopped by the capacitive plate, it gives up its KEM field energy. That energy is released and becomes charge between the two capacitive plates and builds up as a charge with a distinct north and south pole and a plus and minus orientation to its fields, to its charged boson fields, as you can see in the geometry there. The application of AC allows the energy to flow through, but it blocks the flow of electrons from flowing through, so it blocks DC. Again, Tetryonic field theory shows you the reasons behind the displacement current as well as the geometry of the charge that is built up. If a capacitor is short-circuited, all that energy, the charge, is released instantaneously. Distributions and uncertainty. Again, the distribution of energy in an equilateral geometry is such that it creates a normal distribution of energy. If you were to plot the plus and minus energy quanta on the right hand side drawing, or any equilateral energy geometry, you will end up with a normal distribution. And likewise, as evidenced with the KEM fields, any attempt by an observer to observe a particle by measuring it with light or detecting it will either add or remove energy from its KEM field and affect the measurement taking place. So in this case, the energy distributions of the KEM fields are shown to tie in beautifully with Bell's theorem and Heisenberg's uncertainty principle so far as measurement is concerned of physical systems at the quantum level. Again, the KEM fields, as we've noted before, as you add baryons, or as you add nuclei together on top of each other, they act like series batteries, increasing their energy level as illustrated with the color code on the left hand side of the illustration. As electrons bind to these 8 energy levels in the atom, their KEM energy fields is affected, in turn affecting their rate of spin, or the linear momentum within the KEM fields, increasing their velocity. The energy content of the KEM fields follows the E equals mv squared formulation, with half the energy being kinetic energy, the other half being the magnetic moment of the electron as it rotates within the atomic nuclei. All energy resulting with spectral lines is either released as electromagnetic induction with charged bosons, or as photons, where W plus and minus bosons come together to form photons. The bosons obviously add up into square energy fields as illustrated there, whereas the photons combine to form diagonal energy geometries as noted there. And again, as noted at the top, a neutral boson of plus and minus energy quanta has a completely different geometry to that of a neutral photon. They both have two quanta, but it's the arrangement of their quanta geometries that determines whether they're a Z boson or a neutral photon. Photons themselves are electromagnetic fields. They radiate bilaterally, that is, they have two charged geometries, both of which contain energy momenta, and they radiate out at the speed of light in a vacuum. The measurement of these fields can take place as indicated at the bottom, either through their electric component or through their magnetic component, but in both cases there exists magnetic and electric field components to EM fields. Photons are 2 pi geometries, or tau pi geometries. They consist of a positive charge boson and a negative charge boson, and if you look at the electric energy flux as drawn on the bottom diagrams, you'll note that the electrical energy within photons circulates around the transformer coupling, or the two inductive coupling axis, in a way that simulates or resembles the infinity symbol. It's a continuous loop of energy. The energy is equal between positive and negative and circulates continuously between positive and negative electrically. Physically, they are just two charged geometries back to back. The photon, interestingly enough, as indicated on the right, has a distinct magnetic dipole. Every photon has a magnetic dipole, and these magnetic dipoles, along with the electric fields, are what enable photons to join together to form electromagnetic waves. The strength of the E and the M fields is proportional to the energy quanta within those fields. It can be viewed as E equals HF, or as two connected charged bosons, plus and minus charges, with the energy content per charge or voltage in each case. In both cases, they create electric fields of force through their energy momenta, as well as magnetic fields of force through the magnetic dipoles. If you view a point in space and allow a tau pi or 2 pi photon geometry to pass by it, you'll find that the diamond and triangular geometries of the electric and magnetic fields over a measurement of time will create sine waves of electric and magnetic fields that are 90 degrees out of phase with each other. These are the traditional sine waves that are measured and drawn for electromagnetic fields in Maxwell's transverse waves, although in the case of physical geometry of photons, the electric and the magnetic dipole arrangements depends on which side you view the photon from. One of the more famous formulas of math is Euler's formula that relates sine and pi and exponential numbers together in one equation along with irrational numbers to create one formula. Applying Euler's formula to the pi geometries of energy quanta within charged fields gives us not only a geometric explanation or representation for Euler's formula, it also gives us an explanation for Euler's formula where it's solved to be EI pi equals -1, or it's solving for the square root of -1, which most people or mathematicians will point out you can't solve for a square root of -1. If you apply Euler's formula to the pi geometry of charged fields, you can in fact solve for the square root of -1. It simply becomes the linear momenta of a negative charged field. All photons possess kinetic energy, or are KEM fields. As we've noted before, KEM fields are charged field geometries, equilateral geometries. In the case of a photon, they are simply two charged fields inductively coupled so that they can radiate in both directions at the same time. All the formulas for mass, momentum, kinetic energy apply to the Tetryonic geometries of photons and are explained on this page. Photonic energy can be applied to the kinetic energy or the KEM fields of electrons, whether they're bound to nuclei or free electrons, and that energy will be absorbed into the square energy fields of the electron's KEM field. Changes in the energy field of electrons' KEM fields give us the spectral lights, in particular the spectral lines that are mentioned in this page here. The geometries fully represented by the equilateral KEM fields, and in fact we'll go into it step by step for each spectral line. The energy transitions between square energy levels of the KEM fields will be shown to represent the spectral lines and to give the exact answers in each case. We can then show through mathematics, for those mathematically inclined, that Rydberg's constant RH is in fact just another way of rewording the linear momenta, or the square root of any KEM energy field. So any electron in motion in the atom will have a linear momentum component to its energy field, which is the square root of the KEM field. We can then break that energy field up using Planck's constant and the speed of light to give us a formula for wave numbers, and these wave numbers then give us the wavelength and the frequency of the light emitted by each transition in the atom from one energy level to the other within that atom. In all cases, the energy change is in the KEM field. The matter of the electron remains invariant to the velocity changes in the energy that's added or taken from the system. This picture shows how charged bosons on the left hand side of the page, which are calculated by N Planck nu, come together to combine to form light frequencies, which are whose energy levels are calculated using NHF. Again, of note, you cannot say that charge or H nu equals HF. That's equivalent to saying 1 equals 2. It always takes 2 charges to form 1 photon of energy. The bottom of the page, we have our equilateral energy or KEM energy triangle, separated slightly into the various bosons that make up the energy or the quantum level jumps within that energy field. And to the left and right, we see the various numbers of quanta that have to be released for an electron's KEM energy field to transition from one quantum level to the other. For example, in the case of a Lyman transition, if you look at the top left hand side of the numbers, you'll see that a Lyman transition to go from level 1 to level 2 requires 36 photons. To go to level 3 would require 96 photons. So as the electron jumps or transitions from one energy level to the other because of the energy level of the atom that it's in, it has to give up or receive specific amounts of energy in the form of bosons. In this case, you can see the bosons there, and each energy field has to give up exactly that amount, or it can't jump from one energy level to the other. And putting in energy that has one quanta too many doesn't work. They are specific energy levels, and that's what led to Einstein's photoelectric effect. Again, here we've illustrated in the center of the page the electron with its KEM field. You can see that it has a charge on the bottom below the KEM field of 12 for the electron, and it has a mass of 12N. They remain invariant. What changes, as indicated at the top of the KEM triangle, is its kinetic energy. The KEM field itself, the energy within that field. Then you can add the mass of the field to the matter, or the mass matter of the electron, to give you a relativistic energy, or total energy of the electron. Down the right hand side, we've separated them. We've shown you the electron as a rest matter, the electron with its kinetic energy field in motion, and then a more detailed view of that kinetic energy field with its kinetic energy and its magnetic dipole orientations. The formula for a KEM field, or for any kinetic field, is simply mv squared, or matter velocity squared. The mass matter of the electron in motion by its velocity squared is how much energy is within its KEM field. And consequently, if you want to accelerate the matter of an electron to a certain velocity, you need the energy that's in that field to do it. When you measure a wave of light, an electromagnetic wave, you can measure it one of two ways. You can measure the transverse mass or transverse energies of the wave, or you can measure the longitudinal waves or the longitudinal masses of the electromagnetic wave. Tetryonic geometry helps to clarify one from the other once and for all. If you measure transversely, you're measuring the bosons, and their energy is given by the formula Planck's constant mu, or an odd number, odd pi geometries. If you measure the transverse, the longitudinal component of the wave, or the direction of the wave as it travels towards you, you're measuring the photons, or the energy momenta of the wave as it approaches you, in which case the formula is given E equals HF, or Einstein's calculation. The difference between the boson measurements and the photon measurements, or transverse and longitudinal waves, is what led to the confusion with Einstein and Planck's relationship for the energy of light. Planck was measuring the boson energy content, Einstein was calculating for the energy content of photons, or the frequency. Again, it takes two charged quanta, to make one photon. They're not equal, and you can't describe them as being equal. Looking closer at the electromagnetic waves, looking at the equilateral geometry specifically of the quanta within each wave. Each electromagnetic wave has a diamond shape because of its even numbered quanta. It's made up of photons, two quanta per photon. Multiples of 2 create even numbers. The amplitude of the wave, or the square root down the middle, gives us the probability. So if you had a electromagnetic wave that had a amplitude of 8, as in the top right hand corner, the energy quanta in that wave, there'd be 64 of them. So to find the probability of any particular energy or any particular number of quanta is simply the probability as it's been color coded there. The highest probability of the wave obviously is the center of the wave, which is the linear momentum of the wave. And as you move outwards to the lower probabilities of detecting the wave, you come to the edge of the wave. So the probability of the wave simply follows the equilateral geometry of the energy quanta in the wave, and that gives us the statistical probability mechanics of quantum electrodynamics, or wave functions, as most people refer to them. Electromagnetic waveforms themselves, as we've discussed, can be made up of bosons or photons, and likewise they can propagate in various fashions. In the case of electromagnetic waves made by oscillating charges back and forth in an AC field, we create transverse waves of frequency measurement, which are normally measured with frequency. In the case of spark gaps, where the energy is released in a very short duration within a charged geometry, we create longitudinal waves, which are the waves that Tesla tried to describe in his work as scalar waves or longitudinal waves, and as they're the waves that he measured, but he measured them differently from transverse waves. They're best measured as voltage fluctuations, because they release their energy in a short term within equilateral geometries or charged geometries. That's a measure of voltage. It's just energy per charge, voltage, a measurement. Whereas in the case of transverse waves, we measure them as they come in, and we measure the frequency or the number of quanta per second as the waves come in, and that's the frequency measurement. They are identical waves. Where they differ is in their orientation. The transverse waves stand upright, just as the wave is drawn on the page there, the equilateral central picture. That would be the geometry of a transverse wave coming towards you. If you were to view that, or if it was a longitudinal wave of the same energy, that upright triangular geometry would in fact rotate towards yourself, so that it's like a knife pointing directly out of the page, coming towards you, in which case the energy momenta will be pointing at you like a knife, and that would be measured as voltage rather than frequency. And again, the main point here is that the energy momenta is pointing towards you, so that it can do a great deal more damage than pointing upright. Rydberg's formula, as we've mentioned, Rydberg's formula, or constant, is just another way of re-expressing the linear momenta of a KEM field, KEM energy field, and using Tetryonic geometry of equilateral energy within the KEM field, we can rewrite all the equations relating to Rydberg's formula and constant and spectral lines. In fact, we won't go into it here, but you can look at the page, and we'll discuss it further as we go through. Again, the energy of any KEM field pictured in the middle here is directly proportional to the number of energy momenta within that field, or the Compton frequency, the number of quanta, square number quanta, energy quanta within that field. When that energy is released as it transitions from one square energy to the other, as a kinetic energy wave, it releases specific frequencies of light, or specific quanta of light, which are then measured either as a frequency, or in the case of Balmer's spectral lines, can be visually seen as colors. All the absorption and emission lines of electrons within atomic nuclei can now be drawn as equilateral energy geometries that transition between one boson or quantum level and the other, between their various square energy numbers, adjusted on the side there instead of square energy numbers. Obviously, because it's matter times velocity squared, we have 12 times the velocity. So 12 times 1 is 12, 12 times 2 is 36, and so on, right down to 12 times 8 squared, which is 180. So that's how many quanta we have to give up in each one to achieve our energy transitions in atoms. Rydberg's constant then can be exactly calculated as a measure of linear momenta, hence why the numbers appear in pink on this page, and as drawn as the square root of the KEM field energy triangles here. You can see that in each case of the pictures here, the electron is transitioning to a specific energy level. In the case of the top left hand side, it's the N1 level. Next down, it's transitioning to N2, and in the case of N2, these energy transitions are simply changing the quantum energy from one squared energy level to the next, and you might be starting at energy level 8. You're getting rid of all that energy so that you end up at energy level 2. Those particular transitions are Balmer transitions. Each spectral group of energy transitions down to a certain energy level have been given names. The only one out of the box, the odd one, is the final energy transition, which I've left as an unnamed one, but it's this transition on the top right hand corner. It's jumping from level 8 to level 7 within the atomic nucleus, so that remains to be named by physicists and scientists down the track. But it's shown in Tetryonic geometry to exist. It's normally lost because there's so many spectral lines within the measured light coming out of an atom that you don't notice it. Again, the energy content of particles in motion is all stored in their KEM fields. The energy added to a particle to accelerate it to a speed is stored in the KEM field and measured as mass or energy, depending on whether you just measure the energy content or whether you measure the energy content per unit of time. One of the highlights that come out of this that will be discussed further in cosmology, in the cosmology book, is the relationship of mass to matter. Everyone's familiar with Einstein's E equals mc squared, where m is E divided by c, or energy per second, or energy per c squared radius, or geometry in the case of Tetryonics. In fact, what happens is when you do the calculation for matter, you find that matter, the energy of matter, is measured per c to the fourth. So E per c to the fourth is the matter content, or the mass matter content of any physical object. This then gives us a relationship between radiant mass, or mass energy, and matter of c squared. A little bit confusing to go into here. As I said, it's handled in greater detail as a consequence of developing quantum gravitation and combining general relativity with quantum relativity, where we have to be very specific in the difference between mass and matter. But suffice to say that E equals mc squared still applies as it always has, but using Tetryonics we now show that the energy content of matter is E per c to the fourth, and obviously straight algebra gives you the relationship between mass and matter as being c squared. So where Einstein says E, what's a good way to say, M, in Einstein's case you would say M as the top here is energy divided by c squared. You can in fact also say that matter is E to the c to the fourth as it's written at the bottom. Or alternatively you can say E equals mc squared, or E equals mass times the square of the speed of light. But equally, if you say E equals m divided by c squared, you're describing the energy content of matter. Again, I'll say that aloud because it's not written there. E equals m divided by c squared, so you're dividing mass by c squared to get E divided by c4. So the relationship between mass and matter is c squared. That's drawn visually throughout Tetryonics as the difference between seconds and seconds squared. 1 second is just c squared as it's drawn here at the top right around the energy to give us mass. If you were to draw a second circle, or c to the fourth for seconds squared for matter, you would then have c to the fourth. So again, the geometry ties one to the other right through. The spectral colours of light are all now explained one after the other. These sequence we'll run through rather quickly here because you can spend time looking at the numbers, doing the calculations. In fact, I've spent quite a lot of time looking at the numbers and doing the calculations backwards and forwards to develop these illustrations. But in essence, on the left-hand side, you have all the possible energy states that the electron can be in within the atom, and the final one that it's seeking. They're then drawn again with the numbers of quanta that have to change in order to reach those energy levels. These are represented on the right hand side as an equilateral KEM field with the formulas HF divided by N squared, which is just the transition from one energy level to the other. The number here is just the frequency of the light, or the wavelength of the light in this case. Again, the KEM field is given as an expression of Planck's constant with Rydberg's formula. Rydberg's constant, it's just a measure of the C by Rydberg's is frequency. It's a measure of the linear momentum. How many energy quanta are in that field. You can go through and do the calculations, and I encourage you to do so when you want to get a really good feel for how these transitions take place. But in doing so, you'll find that the standard formula for calculating it is listed on the right hand side. It's for the wavelength, it's just Planck's constant divided by the linear momentum of the energy field, Rydberg's constant again. Or if you divide the linear momentum of the field by Planck's constant, you'll get the wave number, which is what Rydberg's constant normally calculates for. When you apply Tetryonic understanding of mass and matter, in particular its understanding of Planck's constant as being a measure of mass times angular momentum, or equilateral geometry, you discover that you can strip mass or energy content out of these right-hand formulas that are normally used in quantum mechanics or QED, and in fact create even more general formulas for all of physics and quantum electrodynamics by simply using quantized angular momentum either divided by c, which will give you momentum, or c divided by quantized angular momentum will give you the wave number. All these things, in fact, if you just look at mass times angular momentum, as I've indicated here, you get mass angular momentum is Planck's constant, and mass times c is momentum. So all these formulas here have in common, what they have in common is energy per c squared, or energy geometry. Stripping out the energy measurements, we have the geometry measurements, and it's the geometry measurements that show us that all of light that we get from atoms is all geometric. It just reinforces that Tetryonics, with its geometric approach to energy, is the correct approach, because we've not only explained quantum electrodynamics and all the energy in quantum mechanics, but we've gone one step further and simplified the formulas used for all these transitions. Again, what we've just viewed there is Lyman's transitions. Balmer's transitions are identical. The only difference is that they're jumping down to an energy level of 2, and all the transitions in between. So all that changes is the energy content in the KEM fields, and obviously the wavelengths of the light that are required to transition from one energy level to the other. We also have Paschen series of spectral lines. The bracket series of spectral lines, there's 4 transitions there. The Pfund spectral series has 3 transitions. And the unnamed series has a single transition within it. That's just another view of the different ways it works. When you look at the QED ebook, you'll discover that there's 4 or 5 pages to all of these transitions, some explain the math, some go into additional geometry of these transitions. In summary, what you have here is the KEM fields along the bottom with the energy levels of the photoelectrons above it, and all the spectral lines of light that can be created within atoms, all from the equilateral geometry of the energy in the KEM fields. The photoelectrons, or the electrons that are used in the photoelectric effect that Einstein made famous when he got his Nobel Prize for the photoelectric effect, are now finally given real geometries. The matter of the electron is seen here as a 12 pi geometry. The energy content of the kinetic EM field is shown with its equilateral energy quanta. The quantum levels, or the transverse energy levels of the KEM wave, are shown. The linear momentum of the particle in motion is revealed as the square root of the KEM field. You also see the kinetic energy, the neutral kinetic energy component is the electric component of the KEM field, and the magnetic moment of all charged particles in motion is revealed to be just half of the energy of the KEM field again. Using Tetryonics, we can now define the mass matter of particles. We can define the charge of particles. We can define the relativistic energy of the particle with its matter, along with its kinetic energy and magnetic moment, all in one geometry. And in doing so, we can rationalize a lot of formulas like Rydberg's formula and explain things that could never have been explained using mathematics, and have stood for decades without being explained. One of the final things we'll go into here is the coupling constant. Maxwell was a Scottish mathematician who firmly believed that if you create something mathematical, you should be able to build a physical model of it. To that end, in his notes in the center of this page, you'll see an illustration where he attempted to explain the lines of force in electromagnetic fields. Faraday described the lines of force. Maxwell attempted to portray them mathematically with his equations. Once his equations were formed, he then attempted to build a mathematical model of how these fields conduct their force, so to speak, how the effective force moves through thin air, through these fields that Faraday had so successfully described. The closest he came was that middle picture, and he could never fully do it. But if you view electromagnetic fields or equilateral fields, the KEM fields, with their corresponding rotational vector for their equilateral, for the quantized angular momentum, you can then suddenly develop a picture of clockwise and anti-clockwise circular rotations of energy. And in fact, were you to build these clockwise and anti-clockwise rotations of circular energy or angular momentum, you would find they'd all rotate. This top one, if it rotated, would cause all the others to rotate, so that this bottom one also rotated in the right direction. The positive ones at all times will rotate in the clockwise direction, and the negative ones at all times will rotate in the negative direction. So by using the energy flux rotations of quantized angular momentum, where we know that they're actually triangular geometries, we can in fact fulfill Maxwell's desire to create a physical model of lines of force in electrons, in electronic KEM fields, or fields of force. It's the same rotations, fluxes of energy, which are in reality triangular fields, that convey the force of one electron to all the other particles that are around it. These fields spread out at the speed of light, so 1 second after this field was created, it's almost reaching the moon in dimensions. But all these little circular fluxes of energy exist, as do all the energy momenta that we've described using Tetryonic theory, and they give it substance, they give it the force that we've often spoken about. Same fields are drawn here, again at the bottom of the page, with their circles, as well as their true electromagnetic field geometry, and the energy momenta of the KEM field is drawn as well. When these two fields at the bottom overlap each other or superposition, it's a KE, or a kinetic energy field, squared. In effect, they're the electric field components, or the kinetic energy field, kinetic energy components of the KEM field, squared. One field times the second field is the square. So we have a clear demonstration geometrically here that between two charged particles, you have a inverse square force between the two that's proportional to their charges, and it's not affected by the magnetic moments of those two charged particles, because the magnetic fields, or the magnetic moments of those two particles, never come in contact, whereas the electric components do come in contact, and the energy momenta of those fields interact to create the force. That's a geometric description of Coulomb's force law. The same geometry applies in the case of gravity to Newton's force laws. So where you see a diamond-shaped field, you know that you have a inverse square force at work between two objects. These two triangular fields are obviously just kinetic energy fields, so the kinetic energy where they overlap is half of the energy of the KEM field, so it's the square of the momentum divided by 2, or it's half mv squared. So you square the kinetic energies, and you've got the force of interaction between both particles. This kinetic energy, squared kinetic energy field, which are normally described with virtual particles in QED, are now given real form, real geometries, and energy momenta with direction in order to interact. And KE squared can be rewritten as mv squared squared, or m squared velocity to the fourth, and or velocity, momentum velocity squared, or momentum squared velocity squared. In both cases we divide it by 2 because it's only the kinetic or the electric field component that's superpositioned. That formulation there is normally incorrectly written in physics in a number of places as the relativistic energy momenta, kinetic energy momenta formula, normally in the right-hand angled triangle descriptions that you see around the place. All those right-angled triangles now can be replaced by this diamond-shaped interaction field between two KEM fields, thus getting rid of virtual particles in QED, getting rid of infinities, and giving a clear definition of the physical lines of force between charged particles and matter within the universe. All of our physical constants, the speed of light, alpha, elementary charges, Planck's constant, gravitational constants, all of them are generated from the equilateral geometry of energy. All of our laws of conservation for charge, energy, mass, momentum, all of the conservation laws come about because equilateral geometry is quantized. All of energy is broken up into smaller and smaller equilateral geometries, and it's the symmetry of the equilateral geometry that gives us conservation laws, gives us the dipole, gives us the inverse squared law for the electric fields versus the inverse cube law for magnetic dipoles. They all come from equilateral geometry, and all their formulas and their reasons for being can now be resolved back down to the simple geometry of Planck's constant, or the Higgs boson, or just plain equilateral energy, or mass if you measure it per unit of time. Again, breaking up Planck's constant, the absolute quantum of work and energy in our universe, we know that it's now been shown that it's a measure of mass or energy per c squared, as well as equilateral geometry or angular momentum. It's always been combined as one, when in fact they're different measurements of two different aspects of the same thing. The alpha, which is the capital A standing for quantized angular momentum, can now be shown to be the basis of a number of other important physical properties that have been hidden from us using mathematics. In particular, the quantized angular momentum, or the equilateral geometry of energy, gives us the geometry of photons, their direction of propagation, all those sorts of things. But more importantly, it gives us charge. Without charge, the particles wouldn't interact. Without their specific geometry of electric fields and magnetic fields, they wouldn't be able to come together at different ways in different shapes to create matter and to create force interactions. So historically, Planck's constant, written as h, has hidden the fact that equilateral geometry plays a role. Even if it had been split up in the math, which people do suggest from time to time, into mass with angular momentum, without realizing that a equilateral triangle is a measure of square geometries or square numbers, you would never understand that the quantized angular momentum is an equilateral geometry as opposed to a rotation about a point. So Planck's constant's hidden, has a hidden property. The property is the angular momentum, or the quantized angular momentum, which is in fact its geometry. As we've mentioned, the diamond-shaped superposition fields give us our lines of force, or our E-squared fields. They create coupling constants, or the coupling constants give us the strength of the force between particles. They're responsible for the strength of the electrons and the protons' charges, how they interact, how strongly they interact, and they've been a source of bewilderment and mystery for years. Mathematicians have approached calculating or finding out what causes the coupling constant from the side of mathematics, but as with the mathematical approach, firstly they had nothing to base where they were going on, no geometry. Secondly, the number that they were chasing, namely the inverse of 137, cannot exclude kinetic energies for particles in motion. And in fact it is shown that the inverse of 137 that they're basing all the calculations on is in fact the wrong number, because it doesn't exclude kinetic energies. Quantum mechanics, or QED, sorry, to this date, as formulated by Feynman and others, has been touted as the most accurate formula of physics ever developed, accurate to 12 decimal places, because it agrees with this inverse of 137. It's very easy to get a highly accurate agreement with a number that you're looking for when you know the number that you're looking for. In this case, they were chasing the inverse of 137, and they started looking backwards to calculate how they get it, when in fact we'll show you very shortly that the number they should have been chasing, and which is developed strictly from the geometry of Tetryonic theory, is in fact the inverse of 132, as noted down the bottom here. So already, before you even go decimal to 12 decimal or 1 decimal place, you're out. You're out by 5 before you even begin your numbers. So this undermines QED's theory's accuracy. It undermines special relativity. It puts an air of doubt over the whole thing, and the only way you can possibly undermine all that is to have a theory that provides a hypothesis that's falsifiable and that predicts from theory a better result, or a result that at least agrees and explains in a better way. In the case of Tetryonics, from the geometry we can create a better value that ignores kinetic energies, and we develop it directly from theory, from the geometry, rather than chasing it from the mathematics. We can then reapply it, as we do later on in gravitation and in chemistry, to verify that the number that I've created here works for all examples and is in fact exclusive of kinetic energies in a system. The fine structure constant is purely, as I've said, a measure of the force, be it a measure of force between two electrons, two other charges, a distance between them, whatever that force may be it between similar or opposite charges, doesn't matter, because again the difference between similar and opposite charges is just the orientation of the energy momenta in their KEM fields. We can even apply it to gravitation, where we have two bodies of matter with a field of force between them, and we want to know what's creating that force or how strong that force is. In all cases, inverse squared geometries for distance give us diamond-shaped fields. As I've said before, you see the diamond, you know that it's two superpositioned energy fields or electric fields creating force from their energy momenta in those fields. So we do the calculations for the fine structure, we come up with that number there. So all the coupling constants are now shown to be nothing more than two kinetic energy fields on top of each other. 2 by 2 is 4, 2 squared is 4, however you want to do the math. It all works out the same. What the math didn't explain was what the E squared was divided by 4 pi. This formula for alpha shows up everywhere in QED. It's rewritten with other constants in a whole heap of ways, but in essence what they're trying to describe mathematically is two superpositioned KEM fields, two fields of force, one on top of the other, creating a force between two objects. We can do that. We can use the same geometry that we've used throughout in quantum mechanics and QED to show that gravity and Coulomb's constant are in fact the same geometries. Therefore, Newton's gravity is just a weaker form of Coulomb's constant. It'll be shown in quantum gravitation that it's not the same. It's not driven by the same forces, but the geometry works out to be the same, and you can use the geometry to give you the math. In short, Newton calculated for the force between two blocks of matter, and the math uses the same geometry, and that's why Newton's formula for gravity looks so similar to Coulomb's formula for gravity, because it's calculating using the same inverse square law between the two. The proof of the pudding that quantized angular momentum is the coupling constant that I've discussed is when you divide the quantized angular momentum by c squared, like you do for energy to get mass. If you divide the equilateral geometry by c squared, you get the quantum of charge. That number there, Coulomb's, positive or negative, is 1/12 the elementary charge of an electron or a proton. Again, 12 of these make up the geometry of an electron, so 12 times that number will give you the electron's charge. 36 of these will give you the proton's charge. Some people will say, but 36 is different to 12. In the case of the 36 charge geometry of the proton, 24 of them are positive, 12 are negative, so they cancel out. 24 minus 12 gives you plus 12, the exact opposite charge of the electron, showing you that the hidden coupling constant, the hidden alpha constant of all of physics that they've been searching for, is in fact the equilateral geometry of energy. And it's that geometry per c squared, or per second, that gives you charge. Conversely, if you were to swap if you take the alpha constant, or quantized angular momentum, and get the units of that, which is square meters per second, divide it by c squared, you find that you have a unit left over, which is seconds. So quantized angular momentum per c squared is seconds, plus or minus seconds. Again, reinforcing that charge, plus or minus charge, is equilateral geometry and a measure of mass. So you get mass seconds for your current, kilograms per second for your current, seconds per kilogram for your Coulomb measure of charge. We then tidy it all up by simply saying that all of electrodynamics, so far as the motion of particles or the motion of matter, can be summarized as the equilateral geometry of energy within the kinetic energy fields, whereas in quantum mechanics we were strictly related to the geometry of energy within mass and matter, and explaining it that way. This, in electrodynamics, we add the geometry of a kinetic energy field onto the geometry of matter to give us motion, and that's why the definition is between the two. The one final point that I'd like to make is that following the geometry out now, we can obviously show that in the case of equilateral geometries, we can have any velocity between 1 and infinity. All we need to achieve that velocity is the square number of quanta in there. If, for example, we wanted to go to 100, we would need 100 squared quanta to give us enough energy momentum to drive the matter at that velocity. So if you then take that logic further to infinity or whatever number, you can see that we, in fact, with enough energy, can go past the speed of light with any particle. It's just a matter of supplying enough energy per second to create energy momentum per second to create the impulse momentum for that particle to go at that speed. Once it's at that speed in space, it will naturally continue at that speed until you go to slow it down by applying the reverse energy to that same matter geometry to slow it back down. And that concludes equilateral energy in quantum mechanics and QED. Chemistry and other discussions will be available online over time.